Hello, everyone. You are listening to Uncomfortable Truths with Euclid Phoenix, where I talk about politics, religion, and other BS that I find interesting. This segment talks about black holes and astronomy, the dark engines of the universe. Black holes are no longer theoretical curiosities. Once considered bizarre predictions of Einstein's equation, they are now among the most important and best studied objects in modern astronomy. They shape galaxies, power the brightest objects in the universe, and push physics to its limits. But what exactly are black holes, and why do astronomers care so much about them? A black hole is a region of space-time where gravity becomes so strong that nothing, not even light, can escape. At its core are two defining features. First, singularity, a point or region of extremely high density where known physics breaks down. Secondly, the event horizon, the boundary beyond which escape is impossible. Once something crosses the event horizon, it is effectively cut off from the rest of the universe. This doesn't mean black holes are cosmic vacuum cleaners sucking everything in. Objects can orbit them just like planets orbit stars if they are far enough away. How black holes form. Most black holes form from the death of massive stars. When a star much larger than our sun runs out of nuclear fuel, it can no longer support itself against gravity. The core collapses inward. If the mass is high enough, it compresses into a black hole. This process often creates supernova explosion, briefly outshining entire galaxies. Types of black holes. Astronomers categorize black holes based on their mass. 1. Stellar mass black holes. Formed from collapsing stars, typically 5 to 100 times the mass of the Sun. Supermassive black holes, found at the center of most galaxies, millions to billions of times the Sun's mass. Our galaxy, the Milky Way, contains one called Sagittarius A. 3. Intermediate black holes, possible, between stellar and supermassive, still under investigation. Primordial black holes, hypothetical, may have formed shortly after the Big Bang, could range wide in size. How we detect black holes. Black holes themselves emit no light, so astronomers detect them indirectly. 1. Accretion disks. When matter falls toward a black hole, it forms a spinning disk that beats up and glows immensely. These disks can emit X-rays, gamma rays. None of the brightest objects in the universe, quasars, are powered. Some of the brightest objects in the universe, quasars, are powered this way. Stellar motion. If a visible star orbits an invisible object, astronomers can calculate its mass. If the mass is extremely high and compact, it's likely a black hole. This is how Sagittarius A was confirmed. 3. Gravitational waves. When black holes collide, they send ripples through space-time. These were first detected in 2015 by LIGO, confirming a major prediction of relativity. 4. Direct imaging. In 2019, scientists captured the first image of a black hole's shadow using the Event Horizon Telescope. This wasn't the black hole itself, but the glowing material around it and the silhouette of the event horizon. What happens near a black hole? Black holes produce some of the most extreme environments in the universe. Spaghettification. Yes, the name is real and accurate. As you approach a black hole, gravity at your feet is stronger than at your head. You are stretched into a thin shape. Time dilation. Near a black hole, time slows dramatically. To an outside observer, you appear to freeze near the event horizon. To you, time feels normal. This is one of the most extreme examples of Einstein's relativity in action. Relativist jets. Some black holes shoot out massive jets of energy at near light speed. These jets can extend thousands of light years. They play a major role in shaping galaxies. Do black holes destroy information? This is one of the biggest unresolved questions in physics. According to quantum mechanics, information cannot be destroyed. But if something falls into a black hole, where does this information go? This leads to the black hole information paradox, a problem that has challenged physicists for decades. The black hole information paradox, where physics breaks down. Black holes are already strange. They bend time, trap light, and warp space itself. But buried inside them is a problem so profound it threatens the foundations of modern physics. Do black holes destroy information? If the answer is yes, one of the most important laws in physics is wrong. If the answer is no, then our understanding of black holes is incomplete. This is the black hole information paradox, and it remains unsolved. What do physicists mean by information? In physics, information doesn't mean thoughts or memories. It means the exact state of a system, the position, energy, and properties of every particle. If you know all the information about a system, you can, and in principle, reconstruct its past, predict its future. This idea is built into quantum mechanics, which says information is never destroyed. What happens when something falls into a black hole? Imagine throwing a book into a black hole. That book contains words, ink patterns, molecular structure, atomic arrangement. All of that is information from the outside. The book crosses into the event horizon. It disappears from view forever. So where does the information go? The classical answer: it's gone. According to classic physics, the black hole absorbs the matter. Everything is compressed toward the singularity. The information is effectively lost. And that seems fine until quantum physics enters the picture. Hawking radiation changes everything. In the 1970s, Stephen Hawking made a groundbreaking discovery. Black holes aren't completely black. They emit tiny amounts of radiation due to quantum effects near the event horizon. This is now called Hawking radiation. Over time, the black hole loses mass. It slowly evaporates. Eventually, it disappears. Here's the problem. Hawking radiation appears to be random. It does not seem to carry any information about what fell into the black hole, the structure of the original matter. So when the black hole evaporates completely, the information is gone. Why this is a crisis. This creates a direct conflict between two pillars of physics. Quantum mechanics says information must be preserved. The universe is fundamentally reversible. Black hole physics, as Hawking described, says information is destroyed. Both cannot be true. That's the paradox. Why physicists care so much? This isn't just a technical issue. If information can be destroyed, quantum mechanics is incomplete or wrong. If information is preserved, our understanding of black holes is incomplete. Either way, something fundamental about reality is missing. Proposed solutions. Over the decades, physicists have proposed several ideas. None are fully confirmed, but some are more promising than others. Information escapes through Hawking radiation. Maybe Hawking radiation isn't truly random. It might subtly encode information, leak it out over time. This would mean the information is preserved but completely scrambled. Two, information is stored on the event horizon holographic principle. Some physicists propose that all the information inside a black hole is stored on its surface. This is known as the holographic principle. Think of it like a 3D object encoded on a 2D surface. This idea suggests the universe itself might work this way. This is one of the most influential ideas in modern theoretical physics. 3. The firewall hypothesis. This is a more radical idea. It suggests the event horizon is not smooth. Instead, it's a high-energy firewall. Anything falling in would be destroyed instantly. This preserves information but breaks another principle of relativity. So again, physics conflicts with itself. 4. Black hole remnants. Another idea, black holes don't fully evaporate. They leave behind tiny remnants. These remnants could store information. The problem, we've never observed such objects. It raises new theoretical issues. 5. Information goes somewhere else. Wormholes, multiverse ideas. Some speculative theories suggest information exits into another universe or through a wormhole. This connects to the idea like white holes, quantum space-time networks, but these are highly speculative. Where things stand today, modern research leans toward this conclusion. Information is not destroyed. Recent developments using quantum information theory and gravity suggest that Hawking radiation may carry information after all. The process is incredibly complex, but consistent with quantum mechanics. Even Stephen Hawking later reconsidered his original stance. The bigger picture, the black hole information paradox isn't just about black holes. It's about the nature of reality, whether the universe forgets anything, how gravity and quantum mechanics fit together. Solving it could lead to a theory of quantum gravity, a deeper understanding of space-time, possibly a new view of the universe itself. Final thought. Black holes don't just trap matter, they trap our understanding. And until we solve the information paradox, we're left with a universe that seems to contradict itself at the deepest level. That's not a failure of physics, that's an invitation to go further. Hawking radiation. Do black holes evaporate? In the 1970s, Stephen Hawking showed that black holes are not completely black. They emit tiny amounts of radiation due to quantum effects. Over extremely long timescales, black holes can lose mass, eventually evaporate. For large black holes, this process takes longer than the current age of the universe. Black holes and gravity evolution. Black holes aren't just destructive, they're creative forces in astronomy. Supermassive black holes regulate star formation, influence galaxy shape, control gas flows. Without them, galaxies might look very different. In a strange way, black holes help structure the universe. Are black holes gateways? Science fiction often portrays black holes as portals. In theory, some solutions of relativity suggest connections to wormholes, but in reality, known black holes would destroy anything entering them. No evidence suggests safe passage. Still, this idea continues to inspire both physics and storytelling. Why black holes matter. Black holes sit at the crossroads of gravity, general relativity, quantum mechanics, cosmology. They are one of the few places where all major areas of physics collide. Studying them helps us answer what happens at the edge of known physics. How does space-time behave under extreme conditions? Can gravity and quantum theory be unified? The bigger picture. Black holes began as equations, then they became predictions. Now they are observations, and they continue to challenge our understanding of reality. They remind us of something fundamental. The universe is not only stranger than we imagine, it may be stranger than we can ever imagine. That's it for today. Thank you for listening, and I hope you enjoyed the show.